Objective: explain electron C model and band theory of matter. 2. Describe semiconductor. Introduction: the electrical properties of material play a crucial role in determining their practical application in modern technology. Metal and semiconductor inhibit different electrical behavior due to the nature of their atomic bonding and electronic structure. Understanding concepts such as metallic bonding, the electron C model, and band theory provide a theoretical foundation for explaining electrical conductivity in metal, while the modification of semiconductor through doping enable precise control of charge carrier in electronic application. What is metallic bonding? Metallic bonding occurs in metal. It is the electrostatic attraction between positive metal ion and the localized electron. Metal atoms lose their valence electron. The electrons are free to move through the metal structure. Electron C model. Metal atom release valence electron. Electron become delocalized. Positive metal ion form a lattice. Delocalized electron move freely. Electrostatic attraction form a metallic bonding.
Before we move on to the topic of semiconduction, let me introduce you to the band theory of metals. The band theory is a quantum mechanical model, like the one pictured above, that describes the electronic structure of metals in terms of energy bands and electron distributions. Basically, there's a higher energy band and a lower energy band, and the electron distributions between them. Now, for our next point, the energy levels of valence electrons in metals. This topic right now that we're presenting is focused on metal conductivity, after all, are adjacent with each other, which means adjacent, which forms a continuous band, also known as a valence band, that is overlapped by the next higher energy band known as the conduction band. This overlapping results in free to move delocalized electrons in the crystal structure of the metal. This contributes to the electrical and thermal conductivity. How that does that, we will figure it out. We will explore it in the following slides. Now, if you do not understand at first what valence bands and conduction bands are, then do not worry, we will be explaining them to you shortly. Right now, in fact. Valence bands are energy bands which contain the energy levels of valence electrons. Valence electrons are electrons situated in the outer shell of an atom. You will understand this better if you would look at a picture of an atom. Okay, and there are circles, okay? Electrons in the outermost shell are called valence electrons, and they can be transferred to other atoms when a chemical reaction occurs, when they join together, and so on and so forth. Now, the valence band, okay, can be found beneath the conduction band. Why is that? Because the conduction band has a higher energy and the valence band has a lower energy. So, of course, the lower energy is going to sit beneath the higher energy. The electrons in the valence band are weakly connected to the nucleus of the atom because they have lower energy. They don't stick and are more prone to being transferred. The conduction band, on the other hand, contains the energy levels of unbound electrons, or electrons that are not bound to any specific atom, which means its orbitals are vacant, empty orbitals. It is made up of orbitals in the valence shell and upper empty shell, which are not occupied by electrons. Now, when external energy is supplied, okay, the electrons from the valence band will move upwards into the conduction band. This creates free electrons. And these free electrons, of course, will move to the conduction band. The energy of electrons in the conduction band will be higher than the energy of electrons in the valence band because of it. Now that we have mentioned the valence band and the conduction band, we also need to explain the band gap, also known as the forbidden gap. Now, the band gap is the energy gap in between the valence band and the conduction band. As you can see below, there are different types of band gaps, from none at all, basically overlapping bands, to small gaps, to larger gaps. But what is the importance of the band gap, you may ask? Well, it's used to determine the electrical conductivity of a material and classify them into 3 different classes, which are conductors, semiconductors, and insulators. An explanation will follow on the next slide. Finally, for this part of the presentation, we can now explain to you the differences in the conduction types. As mentioned, there are 3 types: the conductors, the semiconductors, and the insulators. Now, to go into more detail, the conductors are materials which allow electricity to pass through them. Conductors are materials, for example, like copper, the thing in your wires, the metal in your wires. They conduct electricity very well because there is an overlap between the valence band and the conduction band. What this means is they're right on top of each other. So, the energy required to transfer the electrons from the bottom to the top is very, very low. Very low energy is required, so it can conduct electricity better. The same concept applies to semiconductors, which are materials that show conductivity between the conductors and the insulators. They are partially conductive, but also partially insulative. They're not very good conductors, and they're not very good insulators. They're somewhere in the middle of both. They have some specific uses, but we will move on to those in later parts of the slide. Now, semiconductors have a small band gap between the valence band and the conduction band. This small band gap requires energy to pass through, and the more energy that passes through and assists the electrons in moving from the bottom, the valence band, to the top, the conduction band, the less conductive the material is. Finally, we'll move on to the insulators, which also, unsurprisingly, follows the same concept. These are materials that do not allow electricity to pass through them, like graphite, for example. Now, they have a large band gap. More energy is required to pass the electrons through, which means there is little to no electrical activity. Electricity does not pass through. Even if it does, really, you're not going to get that much of it. Now, that's about it for the band theory. Now, we'll move on to the next part of the slides.
Now, I will explain the difference between N-type and P-type semiconductors, which are formed by adding impurities to a pure semiconductor material such as silicon. First, let's look at N-type semiconductors. N-type is formed when we add pentavalent impurities, which are atoms that have 5 valence electrons. Examples include antimony, arsenic, and phosphorus. When these atoms are added, 1 extra electron is left free because only 4 electrons are needed to bond with silicon. This free electron can move through the structure and act as a charge carrier. As a result, the electrical conductivity increases greatly. These impurities are called donor impurities because they donate electrons. The letter N stands for negative, referring to the negative charge of the extra electrons. Next, we have p-type semiconductors. P-type is formed when we add trivalent impurities, which have 3 valence electrons, such as boron, aluminium, and gallium. Because there are not enough electrons to form complete bonds, this creates a missing electron space known as a hole. These holes behave like positively charged carriers and allow current to flow. The impurities are called acceptor impurities because they accept electrons. The letter P stands for positive, referring to the positive nature of the holes.
I am Nursyazwani and I will be talking about doping. Dope semiconductor, chemists and engineers can significantly boost a semiconductor's conductivity by manipulating the quantity of valence electron by producing particular kinds of crystal defects. A semiconductor diode with a junction that can be exposed to light is known as a photodiode, and it is the most often used photodetector for general light detection applications. The junction of a p-dope p-type and n-dope n-type semiconductor makes up the most basic diodes. Next one is semiconductor. Its definition is halfway between metals and non-metals.
So the example of semiconductor is microcontroller, which is a compact integrated circuit that combines processor like CPU, the memory, and also the input-output peripheral, making it suitable for embedded application. For example, the application like medical devices or consumer electronics like remote control or toys. We also have memory card, display drivers, auto drivers, keyboard controller, transistor, and also diode. Next, we move on to the applications of PN type semiconductors. For the first one, diode is used in light emitting diodes, LEDs, where it produces output signals to control devices like LEDs. Next, we have the solar cells, where we use photovoltaic technology. So photovoltaic PV technology is a technology that converts sunlight directly into the electrical energy using semiconductor materials through the photovoltaic effect. How it works: when the sunlight strikes a photovoltaic cell, usually made of silicon, the light energy excites the electron in the semiconductor. So this creates an electric current when the electron flow through the external circuit. So the main components of this is the solar PV cell that converts the sunlight into electricity. We have the battery, which is optional, the charge controller to regulate the power flow, and also the inverter that converts DC electric to AC electricity. We also have the photodetectors, for example like sensors and cameras. And lastly, we have the laser diodes, where we can use to make laser pointers, optical storage device like CD and DVD players, and fiber optic communication. Next, we move to the industries that use semiconductors, for example, the electronics and consumer devices, automotive industry, the telecommunications, there's also in healthcare and medical devices, industrial manufacturing and automation, energy and power systems, aerospace and defense, information technology and data centers, and lastly, lighting industry, LEDs. So next we move on to the discussion. So metallic bonding is explained by the electron C model, in which positive metal ions are held together by C delocalized electrons, allowing metals to conduct electricity and heat and to be malleable and ductile. The charge is spread over a larger distance as compared to the size of single atoms in solids. According to band theory, metals have overlapping valence and conduction bands, enabling electrons to move freely without additional energy. In contrast, semiconductors possess a small band gap and therefore show limited conductivity in their pure form. This limitation can be overcome through doping, where the addition of pentavalent elements produces N-type semiconductors with electrons as majority carriers, while trivalent dopants produce P-type semiconductors with holes as majority carriers. The combination of N-type and P-type materials forms p-n junctions that are essential in electronic devices such as diodes, transistors, and solar cells. In conclusion, the electrical properties of metals and semiconductors can be explained through metallic bonding, the electron-C model, and band theory. The presence of delocalized electrons in metals and the overlapping of energy bands allow electrons to move freely, resulting in high electrical conductivity. In semiconductors, conductivity is initially limited due to the presence of band gap. However, this can be effectively improved through doping. The introduction of pentavalent and trivalent impurities produces N-type and P-type semiconductors with electrons and holes as the respective majority charge carriers. The formation of p-n junction from these materials underpins the operation of many electronic devices, highlighting the importance of these theories in understanding and controlling the electrical behavior of modern materials. These are the references. Thank you for watching. Assalamualaikum.